Can you see the sheet?
Yes, sir, we can see the sheet.
Okay.
Yes, sir.
So
Yes, sir.
in the previous class, I have given you the two definitions. One is the classical definition and another is the relative frequency definition of probability. And we saw that there are certain cases where it is not applicable. It means that they cannot be called formal definitions. Rather, we can consider them as the methods for calculation of the probability. In the real life situation, we will still be using only those two methods of calculation of the probabilities. For example, when we are sure about the equally likely things or when we are doing random sampling, so we will use the classical definition. Similarly, in the cases where classical definition is not applicable, we will go by the experience. That means we will be looking at the outcomes of the experiment conducted over a period of time, and then we will look at the relative frequency. So these are the two methods of calculation of the probability. However, to have a scientific framework, we have the axiomatic definition. In the previous class, I told you that we have a sample space, okay? So let omega be the sample space, okay, of a random experiment, and let B be a event space. So that is of subsets of omega which forms a sigma field. I had given the definition of sigma field in the last class. The reason for considering a sigma field is that we may not consider the all subsets of a sample space, but we will consider only that which are relevant. However, when we consider those which are relevant, we should be able to consider their unions, intersections, complementations, differences, and so on. And the sigma field ensures that such sets will be there. So we consider B to be a, in fact, in a definition of mathematics, we call it a measurable set or a measurable space, but I will not use that terminology here because you have not studied that part. So we say a set function P from B to the set of real numbers is said to be a probability function if it satisfies the following three axioms. What are the three axioms? Let me call it P1, P2, and so on. So P1 is that probability of E is greater than or equal to 0 for all, that is, probability is always non-negative. You cannot have a negative probability. The second axiom is that the probability of the full sample space is 1, which means because omega is actually the sure event. So probability of a sure event is always defined to be 1. And the third axiom is that let EI be a sequence of pairwise disjoint sets in B. In the previous class, I have defined the pairwise disjoint. It means that if I take any two sets, then their intersection is phi. So E1 intersection E2, E5 intersection E10, so all of that will be phi. Then probability of union of EI is sum of the probabilities of EIs. This is called axiom of countable additivity. So you look at this. In order to define a valid probability function, we have a sample space and a corresponding event space. On that we have a function. So from B to R is the set of real numbers. That means, and what are the elements of B? They are events. So for any event, we define a number, a real number, and it is called a probability provided it satisfies these three axioms. One is it should be non-negative. Second is the probability of the sure event is 1. And the third one is that if I have pairwise disjoint events, then the probability of their union is equal to sum of the probabilities. This is called the axiom of countable additivity. Okay, so now I have three entities, omega, B, and P. So this is called a probability space. This P we would calculate using any methodology. It can be relative frequency definition, it can be through classical definition, or it could be through any other subjective method also. But if it satisfies these three axioms, then it is a valid probability function. Is it clear to all of you? Do you have any question about these three axioms?
No, sir.
Okay, so now let me look at some of the properties of the probability function. So using this axiomatic definition, when we are able to define a probability function, then we can look at some of the simple properties which will immediately follow. So for example, let us consider first property, that is probability of an impossible event will be 0. Let us look at the proof of this. In P3, let us take say A1 is equal to omega and A2, A3 and so on. Let us take them to be phi. Okay. Axiom A3, sorry, I have used EI, so let me change it here. E1, E2 and E3 and so on. So E1 is omega, E2, E3 and so on, they are phi. So what will be this left hand side? Left hand side will become omega, because omega union phi and so on. And on the right side I will get probability of E1, that is probability of omega, plus probability of E2, that is probability of phi, plus probability of E3, that is probability of phi and so on. So we will get probability of omega is equal to probability of omega plus probability of phi plus probability of phi and so on. So now Probability of omega is 1, that we already know. So this will immediately imply that P phi is 0. Because there is no other way, because 1 will cancel out and you get P phi is equal to 0. Let us look at the second consequence. For any finite collection E1, E2, En of pairwise disjoint events in B, probability of union EI so this is called the finite additivity, and this is also very easy to show. Again, in P3, let us take, say, En plus 1, En plus 2, and so on equal to 5. Then probability of union EI, I is equal to 1 to N. So that will become I is equal to 1 to N plus probability of phi plus probability of phi and so on. However, probability of phi is already shown to be 0. So this means that probability of union EI so this is finite additivity. So probability function is finitely additive. So it is countably additive as well as finitely additive. So is the proof clear to everyone?
Yes, sir.
Okay.
Yes, sir.
Let us look at the third property. Let F be a subset of E. Okay. Then let us consider, so it is like this. So I have E and this is F. Okay. So what is this portion then? This portion, this will become E minus F. All right. So we can write here E as F union E minus F. These two are disjoint. Okay. Clearly these two are disjoint. So probability of E is equal to probability of F plus probability of E minus F. So this gives you two results. One is that probability of F is less than or equal to probability of E. Okay, that is one consequence. So let me put here star, and also that probability of E minus F is equal to probability of E minus probability of F. So if F is a subset of E, then first thing is that the probability of F will be less than or equal to probability of E. So what does it mean? It means probability is a monotonic function. Probability is a monotonic function. See, this is we are establishing in the terms of axiomatic definition. However, it has its roots to the classical definition. See, in the classical definition, how do you define the probability? You are looking at the favorable number of outcomes divided by the total number of outcomes. So naturally, if the favorable number of outcomes are more, then the probability will increase. Similarly, if you look at, say, relative frequency definition, if the number of trials in which the required event occurs more often, then the probability will be higher. So it's a natural thing that we should have that property, and the axiomatic definition allows that this will happen. And the second one is also of use, that is, if I consider the probability of the difference of two events, then it is equal to the probability of difference of the probabilities, provided one of them is a subset of another. Okay. Let us look at next one. Since you always have that phi is a subset of E is a subset of omega for any E, it implies that probability of phi is less than or equal to probability of E is less than or equal to probability of omega. That means 0 less than or equal to probability of E less than or equal to 1 for any event. So when you are calculating probabilities in a problem, you should not get probability outside the interval 0 to 1. Many times I have seen in the exam students get a negative probability, or sometimes they get a probability something like 5 by 2 or 11 or something like that. So you know that probability should always be between 0 and 1. And next consequence is again very simple. What is the probability of complementation? So if I look at omega, omega is A union A complement, okay, for any A. So this means that probability of omega is equal to probability of A plus probability of A complement. Now this is 1, so you have probability of A complement and probability of A making up of the total probability 1. Then the next one is the addition rule. Let E and F be any two events. Okay. Then probability of E union F, that is equal to probability of E plus probability of F minus probability of E intersection F. So let us look at this. Suppose I have event E and event F. Then we can write here this E union F is this entire thing. So I can consider it as E union this portion. What is this portion? This portion is F minus E intersection F. Okay. So we can write here E union F is equal to E union F minus E intersection F. Okay, let me not use this thing because this also looks like complement. Let me put another bracket here. So Now this is a disjoint union because E union F minus E intersection F I have used here. So probability of E union F is equal to probability of E plus probability of F minus E intersection F. But E intersection F is a subset of F. So by the previous rule that if I have F a subset of E, then probability of E minus F is probability of E minus probability of F. So I can use that, and this will give me probability of E plus probability of F minus probability of E intersection F. So this is the addition rule. Obviously, if I have more than 2 events, say 3 events, 4 events, and so on, then there is a generalization of this formula. So let me then give the general addition rule here. Is the proof clear to everyone?
Yes, sir.
Okay.
Yes, sir.
I mean, do you have any doubt in the methodology? See, we just use the axiomatic formulation and whatever basic properties we have already derived. I have just used that only.
So could you just repeat the fifth axiom?
Okay, so let me. Fifth property.
Yes.
Yeah, fifth property is that if I have any event A and then I will have A complement, then A union A complement is omega. So probability of omega is probability of A plus probability of A complement. So probability of omega is 1. So if probability of A is given, then probability of A complement can be obtained as 1 minus. So probability of A complement is 1 minus probability of A. Is that all right?
Yes, sir.
Now if I have more than 2 events, okay, here I have 2, but if I add one more, then what would be the extension of the formula? So in place of 3, if I have 4, if I have 5, and so on. So let me give the general addition rule. So for any events, say E1, E2, En belonging to B, probability of
Sir, someone is removing me continuously from the meeting.
somebody has taken the control.
Yes, sir, you have allowed presenters, like you have allowed all the students to be as presenters. Can you remove the settings like it is happening from
No, I have
the
not done any.
previous
I have.
lectures?
No, I have
Yes,
not
sir,
done
by
any.
default it is like all.
By default, the setting is this. To change that.
Okay, let me see. I don't know where it is.
Remove again, like he is muting me also. Like he is also doing it with Jan. So I am joining it every time, like I can't attend the lectures.
Okay, let me just see. Device settings. I'm not seeing any option.
Sir, it is not possible to change these settings during the meeting. It has to be done prior to the meeting.
Wait a minute. So There should be some option mute all or something like that, but I am not seeing that option. It should be live. Somebody has, I think, removed it from here.
You should make everyone attendance.
Are you, anyway, let me go to the class now. I mean, say. So can you see the presentation now?
Yes, sir, it is visible.
Okay, so let me continue. If you have any difficulty, then you tell me. Otherwise, I will lose time. Okay. For any events, if I have n events, then what is the formula for the probability of the union? So sigma probability of EI, I is equal to 1 to n, minus summation probability of EI intersection EJ, I less than j, then plus triple summation probability of EI intersection EJ intersection EK, I less than j less than k, and so on, plus finally minus 1 to the power n plus 1 probability of intersection EI, I is equal to 1 to n. So it is alternatively plus and minus signs. You have summation, that means you add all of the probabilities, probability of E1, E2, En and so on. Then from there you subtract probability of E1 intersection E2, probability of E1 intersection E3, probability of E2 intersection E3 and so on. Then you add again probability of E1 intersection E2 intersection E3, E1 intersection E2 intersection E4 and so on. And then you subtract taking 4 at a time and so on till you continue, and the last one is the probability of intersection of all of them. Okay, so the proof is by induction. So for n is equal to 1, it is already trivial, because it simply means probability of E1 is equal to probability of E1. For n is equal to 2, we have proved, okay, the addition rule. And so let us assume it to be true for n is equal to, say, r. Okay, so now take n is equal to r plus 1. So what is the probability of union of EI? I is equal to 1 to r plus 1. So what we do, we write it as union of EI, I is equal to 1 to r, union ER plus 1. Now this is union of two sets, and for two sets we have already proved it, so I apply that formula here. Probability of union EI, I is equal to 1 to r, plus probability of ER plus 1, minus probability of union EI, I is equal to 1 to r, intersection ER plus 1. So if you look at this part, on this part, this is only union of R, and we have already assumed it to be true for up to R. So here I can apply that formula, that is EI, I is equal to 1 to R minus summation probability of EI intersection EJ, I less than J, and this is up to R, all right. Then you have triple summation EI intersection EJ intersection EK, I less than J less than K, but all of this will be going up to R only. And so on, minus 1 to the power R plus 1, probability of intersection EI, I is equal to 1 to R. So this is the expansion of this term. Now I have remaining terms, that is plus probability of ER plus 1 and there is one more term, that is this part. Union EI, I is equal to 1 to R, intersection ER plus 1. Now here I can apply the distributive properties of the union and intersection. So this will give me probability of union EI intersection ER plus 1, I is equal to 1 to R. So again it has become union of R events, and I can apply the formula for R because we have already assumed it to be true for R events. So then this is equal to probability of union EI, I is equal to 1 to R minus double summation probability of EI intersection EJ, I less than J up to R I less than J less than K up to R EI intersection EJ intersection EK and so on. Minus 1 to the power R plus 1 probability of intersection EI, I is equal to 1 to R. Now this one I wrote incorrectly. This is EI, I is equal to 1 to R. However, if you look at this, in this one I had an additional term, this one, probability of ER plus 1. So I can adjust with this one. So this becomes sum up to R plus 1. Okay. And now let us look at other terms. So other terms will come from this. Okay. That is the probability of union of R events. So I will apply that formula here, minus sigma. Is this breakup clear to you?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So this is probability of EI intersection ER plus 1, I is equal to 1 to R. And in the next step, it will become double summation I less than J up to R, probability of, well, EI intersection ER plus 1 and then intersection EJ intersection ER plus 1. So I can write it as EI intersection EJ intersection ER plus 1. Okay. EI intersection ER plus 1 intersection EJ intersection ER plus 1. So that I can write like this. Okay. Then the next one will become I less than J less than K. And then next it will become probability of EI intersection ER plus 1, EJ intersection ER plus 1 intersection with EK intersection ER plus 1. I can combine it and I can write it like this: EI intersection EJ intersection EK intersection ER plus 1. and so on. So finally, I will have minus 1 to the power r plus 1 probability of intersection of, well, all will come there. So I'll just put it intersection I is equal to 1 to r plus 1 now, because all of them will come, E1 up to ER and then ER plus 1. So it will become intersection of all of them. Okay. Yes. Is it okay?
Yes, sir. Yes, sir.
Yes, sir.
Now, let us look at these terms. You look at this part here, sigma probability of EI intersection ER plus 1 for I is equal to 1 to R. So what are these terms? This is probability of E1 intersection ER plus 1, E2 intersection ER plus 1, up to probability of ER intersection ER plus 1. Okay. And this is with a minus sign. Okay. And you look at these terms here. What are these terms? E1 intersection E2, E1 intersection E3 up to E1 intersection ER. Then E2 intersection E3, E2 intersection E4 up to E2 intersection ER. So these terms contain all intersections taking 2 at a time up to R, and these give you another term which is involving up to ER plus 1. And this is with a minus sign, this is with a minus sign. So you can add this here and you get then, so this is then becoming sigma probability of EI, I is equal to 1 to R minus R plus 1, and then this is I less than J up to R plus 1 probability of EI intersection EJ. Now let us look at the next one. Next one is here, double summation I less than J up to R probability of EI intersection EJ intersection ER plus 1. So what are the terms here? E1 intersection E2 intersection ER plus 1, E1 intersection E3 intersection ER plus 1, and so on. So taking 2 at a time, and with the third is ER plus 1, and the sign will become plus because this is a minus here and there is a minus here. So it is plus, and if you look at the term here, this is intersection of 3 at a time, but it goes only up to R. So you are adding additional terms which are including the intersection with ER plus 1. So this becomes simply triple summation I less than J less than K. This is up to R plus 1 here. EI intersection EJ intersection EK. So basically what is happening is that the terms which were left out in the initial sum up to R, they are added with the additional term R plus 1 here. Similarly, you look at the last one here, it is minus 1 to the power R plus 1 probability of intersection of all EIs. And there is a minus outside. So if you open that one, then this is becoming minus 1 to the power R plus 2 probability of intersection EI, I is equal to 1 to R plus 1. So we have established the addition rule for general N. I will just mention a few simple results which will also follow from here, but for all of them I will not be giving the proofs here. Okay. So is this proof clear to everyone? We have used the induction.
Yes, sir.
Okay. So I'll just state some more properties without proof. Okay. For E1, E2, En belonging to B, probability of union of EI is always less than or equal to sum of the probabilities. Okay, it is called subadditivity. Okay, again you can prove it by using the previous results, but I am not going to write it here. And then this can be extended to countable subadditivity also. Then next is the Born-Ferroni inequality. Summation of the probabilities minus double summation probability of intersection taking 2 at a time. It is always less than or equal to the probability of the unions, and that is always less than or equal to sigma probability of EI. Okay. Again, I will not be proving all this. So all these results you can prove. I will leave it as an exercise here. Another similar follow-up is the so-called Boole's inequality. So let En be any sequence in B, then probability of intersection of EI's, it is greater than or equal to 1 minus sigma probability of EI complement. So let me prove this one. Of course, proof is very simple because you already have the available tools with you. So probability of intersection EI, I is equal to 1 to infinity, that is equal to 1 minus probability of intersection EI complement. So here you can apply the De Morgan's laws. And on this you can apply the subadditivity. So this will become 1 minus sigma probability of EI complement. So is the proof clear?
Yes,
Yes,
sir.
sir.
Okay. Hello, can you hear me now?
Yes, sir.
Yes, sir.
Okay. Let me just now give some simple exercises on probability. Okay. So you know the famous birthday problem. Okay. All of you have solved this problem. So I'll just look at it. The birthday problem. So suppose there are n students in a class. Okay. So assume n is less than or equal to 365 and no student has a birthday on uh, say 29th February. So I'll just leaving out the leap year here. So we want to look at the probability that what is the probability that no two students share common birthday. So I think all of you know the solution of this problem. So if A is the event that at least at least or let me put A as the event that no two students share a common birthday, then what is the probability of this? I think all of you know the answer to this. That is 365 Pn divided by 365 to the power n. Assuming all dates to be. So here we are using the classical definition that we are assuming that birth for any person is possible on any day. Okay. So it is not based on empirical definition. It is based on the classical definition. All right. If you want, you can expand it and you can write it in a different way. You can write it like 1 minus 1 by 365, 1 minus 2 by 365, and so on. 1 minus n minus 1 by 365. So from here we can also calculate what is A complement, that at least 2 persons share a birthday. Okay. Then of course probability of A complement is 1 minus probability of A. So this formula is anyway, it is well known to you because I think in your class 11, 12 problems you have solved this problem. So I just want to show you the numerical interpretation of this. Let us have a small table. If I have n is equal to 10, then this probability of A is 0.871. The probability that two persons will not have a common birthday, it is quite high, and therefore the probability that they will have a common birthday is much smaller. If I go to 20, then this number becomes 0.589, and at 23 it is actually becoming less than 0.5. So in the common terminology, what we will say, that there is more than an even chance of a common birthday with at least 23 people. So out of 365 days, only 23 people can have the probability of at least one common birthday more than half. And you can just make few more entries here in this table, and you can see how quickly it increases. So the probability with 60 people is almost 1. Okay. For example, your class is a class of 238 students, and there will be multiple students with common birthdays. In fact, there will be students who will have say 7 students may have one common birthday, and so on. So you can actually generalize this. So I put it as an exercise here. So I am putting a general question to you, and you can look at the solutions of such problems. So what is the problem of the probability of 3 persons sharing a birthday, 4 persons sharing a birthday, and so on. So all these questions one can answer, but of course the solutions will be much more difficult to obtain. Okay. Let me look at one or two more simple applications of this. So if 7 balls are placed in 7 cells randomly, then what is the probability that exactly one cell remains empty? So let me just look at the way. So there are 7 cells, okay. Okay. So one of them will remain empty. So we can select that one cell in, because it can be any of them. Suppose we are numbering them 1, 2, 3, 4, 5, 6, 7. So one empty cell can be selected in 7 ways, because 7C1, okay. And if you are placing 7 balls in 6 cells, suppose this one is empty, so then, and each now these cells, all of them are not empty. I mean, in fact, what I am saying is exactly one cell remains empty, so none of these are empty, and you have 7 balls, so definitely one cell will have 2 balls and 5 cells will have 1 each, okay. So now we can say one cell will have 2 balls, okay. Now this particular cell, again out of 6 we have to choose this. This cell can be selected in 6 ways, okay. And there are 2 balls which will be in this cell, so 2 balls can be selected out of 7 in 7C2 ways, okay. And now you are left with 5 cells and 5 balls, so remaining 5 balls can be placed in 5 cells in 5 factorial ways. So the probability will be 7C1 into 6C1 into 7C2 into 5 factorial, and the total number of cases is 7 to the power 7, because every ball can be put in any of the 7 cells. So if you simplify this turns out to be 2160 divided by 16807, which is approximately 0.1285. So this is a application of the classical definition, and we are able to get the answer. Is the solution clear?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yeah, okay. Fine. So I am just giving 1 or 2 problems. Actually, we will be by today evening or tomorrow I will be circulating detailed assignment sheet. So it will have most of the problems like this, but I am circulating it just for your convenience, because you should be able to see that how the solutions are framed here. Otherwise, I mean, these are not very difficult things, but what I am trying to emphasize is that writing down of the details because if you don't write the things, then because many times when we solve the problems, the students are not writing down the events. They are just working on their own mind, and then they are just giving the solution. So that is how the mistakes do happen. Maybe just I'll solve one more problem here. Okay, so let us take so a pair of fair dice if an odd sum or a sum of 4 appears, we stop else we continue. So what is the probability? That 4 appears. So the game is very simple, that you have two fair dice and they are tossed. So if the sum of the numbers is say 3, 5 and so on, then you will stop, or if the sum is 4, then also we stop, otherwise we continue tossing. So what is the probability that 4 appears? So that means the game stops when a 4 appears. Okay. So let us write down the events here. Let us consider say event E, that say odd sum appears. So odd sum, if you look at in the tossing of two fair dice, odd sum can be 3. So 3 can occur if 1, 2 or 2, 1 occurs. Then 5, so 1, 4, 4, 1, 2, 3, 3, 2. Like that you count 11 up to 11. So there are total 18 elements in E. Okay. Because for even sum also 18 elements will be there. Total 36 possibilities are there if we toss a pair of dice. And let us consider event F, and we say sum is 4. Then in this one you will have 1, 3, 3, 1 and 2, 2. Okay. So well, the probability of F can be calculated, probability of E can be calculated. Actually, probability of E is simply half. So when we say 4 appears, then 4 can appear in the first instance itself. The probability of that will be 3 by 36, that is 1 by 12. Or in the first one it doesn't appear. Now if it doesn't appear in the first one, then odd sum should also not happen, 4 should also not happen. So how many possibilities are there? There are total 21 possibilities which are in favor of E and F. So remaining will be 15. That means in the first toss, out of the remaining 15 anything occurs, and in the next one again 4 occurs, and so on. So probability that 4 appears, it can be written as probability 4 appears in first trial plus probability 4 appears on second trial and so on. So then this is equal to 1 by 12 plus, if it appears in the second trial, then in the first trial the probability will be 15 by 36. Of course, this you can write it as 5 by 12. Into 1 by 12 plus 5 by 12 square into 1 by 12 and so on. So of course this is a simple geometric series, so you can easily find out the sum. The sum is 1 by 7. So is it clear?
Yes, sir.
Yes, sir.
The method of solution, is it clear to everyone?
Yes, sir.
Okay.
Yes, sir.
Okay, I will move from the simple things now to another concept called conditional probability. So, what is the meaning of conditional probability? See, if in this problem I had asked what is the probability that 4 appears, then your answer will be simply 1 by 12. But what I am saying now, that the sum of 4 appears in any trial. So that means I am extending the event. So now let us look at say second part of it. Okay. This is saying 4 occurs on the second trial, given that in the first trial neither 4 nor the sum which is odd has appeared. So none of them has appeared. So therefore this is called conditional probability, because it is dependent upon what has happened in the previous this one. So the conditional probability concept is that so let us consider, say, let omega b p be a probability space and let b be any event with positive probability. For any event A, we define the conditional probability of A given that B has already occurred, as probability of A given B. So this is the notation, A given B. It is not A divided by B. It is defined as probability of A intersection B divided by probability of B. You can check that it is well defined. Okay. And from here you can conclude something very quickly. For example, probability of A intersection B is probability of B into probability of A given B. If we assume probability of A is positive, then we can also have probability of A intersection B is equal to probability of A into probability of B given A. You can write in the reverse way also. Okay. Physically, what does it mean? it means I am calculating the probability of simultaneous occurrence of two events, and I am saying this can be calculated in terms of the probability of one of the event into probability of another event conditioned upon the occurrence of the first event. Of course, either way, I mean, there is no sequencing here that A is before or B is before. So you can have these two relations. This relation is actually called multiplication rule of probability. And therefore, you can have a general multiplication rule also. Let A1, A2, and so on be n events with probability of intersection AI positive. So rather than writing down that the probability of A1 is positive, A2 is positive, etc., I am taking the probability of the smallest of them to be positive. So naturally, it will mean that if I consider probability of A1 intersection A2, that will be positive. If I consider probability of intersection of three of them, that is also positive, and so on. Then the general multiplication rule says that the probability of intersection AI, that is the simultaneous occurrence of all of them, can be calculated in terms of occurrence of one given into the probability of second one given the first one into the probability of the third one given the first two, and so on. Well, proof is of course almost trivial, so I will not be writing this here. Okay. Okay, you can write yourself. Is the statement of this general multiplication rule clear to all of you?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Now let us look at the consequence of this conditional probability. So generally what happens, see, for example, if I am looking at this class, the class is happening, okay. Now the class may not happen due to some reason, okay. So what could be the reason? So there can be a network failure, there can be a power failure, or there can be a equipment failure, okay. There can be an equipment failure, there can be a power failure, there can be a network failure. Each of them have certain probabilities, isn't it? The probability of failure of the network could be due to some reason, so there may be some probability, say 0.5. Equipment failure may be 0.3, and say power failure may be 0.1. So when I say what is the probability that there was a failure in taking the class, then it could be either of these things, okay. So frequently it happens that for a particular outcome there can be several causes. So if we consider this cause effect relationship, this is giving rise to two concepts. One is called the theorem of total probability, and a reverse consequence of that is the so-called Bayes theorem. So of course, you know the formulae of this you have done in your school, but here I will be doing it in the axiomatic setup here. So the first one is, let us consider, let B1, B2, and so on disjoint events and probability of Bj's are positive. Okay. Then probability of A intersection B can be written as sigma probability of A of course. So the proof is very simple. So A intersection B we can write as A intersection of union Bj, j is equal to 1 to n. On this I can apply the distributive properties of the union and intersections. Now if B1, B2, Bn are pairwise disjoint, then A intersection B1, A intersection B2, etc. they will also be pairwise disjoint. So probability of A intersection B is the probability of this union. It will become simply the probability of sum. And on each of these terms I apply the multiplication rule. So it is written as probability of A given Bj into probability of Bj. So let us consider a special case of this where B is actually omega. Okay. When B is omega, that means B1, B2, Bn are exhaustive events. Then what will become the left hand side? This will become A intersection omega, that is A itself. So then the statement will become probability of A is equal to sigma probability of A given Bj into probability of Bj. J is equal to 2. Called theorem of total probability. So you can consider it like this, that a particular outcome can be caused by any of the n different causes. It could B1, it could be B2. So what is the probability that it is caused by B1? What is the probability that it is caused by B2, and so on? And probability of B1, B2, etc. is also known. Then this can be evaluated. So this is the concept of total probability. So let me just take up a simple example. So suppose there is a you have some computers, okay. So a computer manufacturer so his integrated circuit, suppose he considers procures ICs from suppliers say B1, B2, B3. Okay. Say with 40% from B1, say 30% from B2, and say 30% from B3. And it is known that suppose 1% of supply from B1 is defective, say 5% from B2 and say 10% from B3. Okay. So he is having the collection of ICs from these three suppliers. So what is the probability that a randomly selected IC from the stock is defective? So this is a classical application of this theorem of total probability, because the total procurement is from three suppliers. So therefore it can be defective if it is from first one, it can be defective if it is from second one, it can be defective if it is from the third one. So the total probability of defective, so if A is the event that IC is defective, it is obtained in terms of these three. J is equal to 1 to 3. So what is the probability of A given B1? That means given B1, what is the probability of defective? It is 1% defective, so 0.01. And what is the probability of B1 itself? That is, because 40% is purchased from B1, so 0.01 into 0.4. From the second one, 5% are defective. And what is the probability of B2? Because 30% is taken from B2. And 10% from the third one are defective. And what is the probability of the third one? 0.3. So this is nothing but 0.049. So there is a 5% probability that IC will be defective. Okay. So you can see, I mean, the different things are there, 1%, 5%, 10%, but depending upon the total procurement from different suppliers, the overall probability of a defective is 0.05. Is the application clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so of course you have solved some such problems in your class 11-12 also, because generally there is a problem on Bayes theorem in your JEE exam. But what is the actual meaning of that I am trying to explain here. And now you look at the reverse of it. Suppose you choose a item and it is defective. What is the probability that it was supplied by first one, or it was supplied by second one, and so on? This result is obtained by the so-called Bayes theorem. It is named after Thomas Bayes. So he is actually in 18th century. However, the result was not popular till very late, and in fact, the people who developed the original probability theory, they did not like this formulation because it is talking about something in the reverse way. Let me explain that. So once again, and one more question that you can see here. I wrote B1, B2, Bn. But in place of B1, B2, Bn, you can also have an infinite collection also, because the result will still be true, because the proof will be still the same. In place of this finite union, you just write infinite union there, and all other statements remain the same. So now I am writing for convenience in the finite case. So let us consider, say, let B1, B2, Bn be pairwise disjoint exhaustive events. So exhaustive means that is union of Bi is omega and probability of Bj is positive. Let A be another event with probability of A positive. Then probability of Bi given A, that is probability of A given Bi into probability of Bi divided by sigma probability of A given Bj into probability of Bj, j is equal to 1 to n. So this is something like asking, suppose the IC that we chose, it is defective. What is the probability that it was supplied by first manufacturer? What is the probability that it was supplied by second one, or what is the probability that it is supplied by the third one? So we are looking at the probability in the reverse sense. That means certain thing which has happened earlier, now I am trying to look at the probability. Because somebody may say that the probability that it was supplied by the first one is 0.4, isn't it? Because probability of B1 is 0.4. But if it is defective, then is it the same probability? So the answer is no, as you can see when we calculate it. Let me give a proof of this Bayes theorem. Of course, it is trivial proof because you already have all the tools available to prove this one. So probability of Bi given A is probability of Bi intersection A divided by probability of A. And in the numerator, you just apply the multiplication rule. So it is A given Bi into probability of Bi. And in the denominator, you apply the theorem of total probability. So proof is just a one-line proof. Okay. However, the consequences of this Bayes theorem are very profound. So the defective IC's example, if I continue. So in the same exercise, suppose a randomly selected IC is found to be defective. What is the probability that it was supplied by B1 or B2 or B3? Okay. What is the probability that it was given by one of them? So if you apply this Bayes theorem, then probability of B1 given A, that is probability of A given B1 into probability of B1 divided by probability of A. Because probability of A we had already calculated. In the numerator, I will have 0.01 into 0.4 divided by 0.049. So this is nothing but 4 by 49. In a similar way, you can calculate B2 given A. B2 given A turns out to be 15 by 49 and B3 given A is 30 by 49. So here you see that although we are taking 40% supply from B1, but the probability of defective from there is much less because it is only 0.01, 1% are defective. Therefore, if it is if a defective IC has been found, then the probability that it was given by B1 is much smaller. It is only 4 by 49. Whereas we are taking only 30% supply from B2 and B3. But if the IC is defective, then the probability that it was supplied by B2 is much higher. It is 15 by 49. And from B3 it is becoming actually 30 by 49. So you can see here the effect of conditioning. That so for example, whenever there is an accident, then government will set up an inquiry committee and they will try to find out what was the cause of the event, what was the cause of the incident, isn't it? So that is something like doing a posteriori analysis. That means afterwards what could have been the reason. So something like a post-mortem, actually you can say in the rough terms. So this Bayes theorem actually allows you to do such things. Nowadays Bayesian methods are used in almost all the branches of engineering, science and technology. You have Bayesian networks, you have Bayesian frameworks, you have so many things which are there. There are in fact specific conferences organized on Bayesian methodologies. And the main reason of popularity of Bayesian in the starting from late 80s and 90s is the use of computational techniques, because earlier the calculations were very complicated, but however when the computers became widely applicable and the algorithms were developed, so nowadays these Bayesian methods are very popular. And the second reason of the popularity is again philosophical also, because earlier in the beginning of the 20th century and when the subject of probability was getting developed, then most of the probabilists and statisticians, they could not understand the significance of posteriori analysis. So they always thought something happens, then the next thing happens. They never thought the reverse way, and therefore they did not like this concept. Okay, let me move to next concept, that is the independence of events. So is the concept of Bayes theorem and the explanation, is it clear to everyone? Do you have any questions?
No, sir.
Okay. Now we consider another thing, that is independence. So it is equally important, like you consider conditioning, similarly there is a independence. So if the conditioning has no effect, then we call the events to be independent. So if the unconditional probability is equal to the conditional probability, then the two events are independent. That means if probability of say A given B is equal to probability of A, then what does it mean? Probability of A intersection B is equal to probability of A into probability of B. Okay. This is also same as probability of B given A is equal to probability of B. Okay. So we consider this to be the definition because it is a more symmetrical statement. Otherwise, I will say A is independent of B. This one I will say B is independent of A. So rather than saying this, we say A and B are independent events. So we say events A and B are said to be statistically independent if probability of A intersection B is equal to probability of A into probability of B. Well, this concept can be extended again if you have 2 events, 3 events and so on. So we say A, B, C are independent. When we have more events, then the number of intersections will be increasing. Okay, so you will say probability of A intersection B is probability of A into probability of B. Probability of B intersection C is probability of B into probability of C. Then probability of C intersection A is equal to probability of C into probability of A. And then you have three of them taken together. So you can have n events, A1, A2, An are independent if probability of AI intersection AJ is equal to probability of AI into probability of AJ for all I less than J. Then taking 3 at a time, AI intersection AJ intersection AK is equal to probability of AI into probability of AJ into probability of AK for all I less than J less than K, and so on. Finally, probability of all intersections taken together is product of all of them taken together. Okay, so these many conditions will come. How many conditions are there? 2 to the power n minus 1 conditions. Okay. Actually, the purpose of independence is that you can calculate the probabilities of simultaneous occurrence of several events if the events are happening independently. So in the physical sense, if the independence is established, then we can apply the statistical independence to derive the probabilities of various events. Let me give one example here. See, for example, if I take any two events, they may be independent, but if I take all of them together, they may not be independent. That may happen actually. So let me just give an example that pairwise independence does not imply mutual independence. Okay, that means all of them are independent. That is not necessary if only I take pairwise, because I have put the conditions together. So if, for example, these three conditions are satisfied but the fourth one is not satisfied, then they will not be independent. So let me give an example of this itself. Let us take, say, okay, suppose two fair dice are tossed, okay, and we have A as the odd number on first dice and B is suppose odd number on second dice, okay, and C is, say, sum is odd. Okay, so let us look at whether A, B, C are independent. Okay, so what is the probability of A? So odd number is on the first dice, that is half. Probability of B is half. And what is the probability of C? That is also half. Okay. If I look at probability of A intersection B, that is equal to 1 by 4. Probability of A intersection C, that is also 1 by 4. And the probability of B intersection C is also 1 by 4. But if I look at, so A, B, C, they are pairwise independent. So if I look at probability of A intersection B intersection C, that is 0. Okay. So this is not equal to probability of A into probability of B into probability of C. So A, B, C are not independent. Although they are pairwise independent, but they are actually not independent. So for overall independence, all the conditions must be satisfied. So let us look at some applications, some examples here I will give. Okay. So is this example clear to everyone?
Yes, sir.
Yes, sir.
Okay. So 6 cards are drawn with replacement from a deck of 52 cards. Okay. What is the probability that each of the that each of the 4 suits will be represented at least once among the 6 cards. So suits means that spade, heart, diamond and club. So let us look at the solution here. So A is the event that all suits appear at least once. Okay. So A complement, see, if I want to calculate directly this probability, one can do it, but it is going to be very complicated because counting the number of cases will be difficult. So you can say that say 4 means like we can have 3 of spades and 1 each of heart, club and diamond. Then we can say 2 of each and so on. Instead, if we can have a simpler formulation by considering the complementary event, A complement is that at least one suit does not appear. Okay. Then we consider here, say B1 as saying spades do not appear. Say I consider B2, say hearts do not appear. Okay. Then B3 say diamonds do not appear. And similarly, say B4 say clubs do not appear. Then we can write here this A complement as union of BI, I is equal to 1 to 4. So in order to calculate the probability of A complement, then I can apply the general addition rule. Okay. So what is the probability of, say, B1? Suppose I say spade does not appear. So that means none of the 6 cards is a spade. Now in a particular drawing, a card is not a spade. What will be the probability? It will be 3 by 4, 39 by 52. Now it is with replacement, so each time it will remain the same probability. So it is 3 by
पाणी असं एक्स्ट्रा मोठं वस्तू आहे ना देग्री आपण आपण भारी लागून घ्या पाणी.
Now this same thing will be probability of, say, B2, same thing will be probability of B3, same thing will be probability of B4 also. Similarly, if I consider, say, what is the probability of, say, B1 intersection B2? That means I am saying spade and hearts do not appear, so it is half. So half to the power 6, and so this will be probability of Bi intersection Bj for all I not equal to j. Of course, we don't have to say less, I mean, we can say less than, actually, that will be enough. And similarly, what is the probability of Bi intersection Bj intersection Bk? That will become 1 by 4 to the power 6. Okay. And what is the probability of intersection of Bi? I is equal to 1 to 4. That will become 0, because it means that none of them appear, which is of course 0. So if I apply the general addition rule, probability of A complement that will be 4 times 3 by 4 to the power 6 minus 6C2, that is 15. So let me write here like that only. 4C2 half to the power 6 plus again 4 1 by 4 to the power 6. Okay, so this you can just put it there. You get this answer as well, after simplification, it turns out to be 317 by 512, which is approximately 0.62. So probability of A then becomes 195 by 512, which is approximately 0.38. Is the solution clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
So I will end my class with one more problem. So 3 players, A, B, and C, they take turns in throwing a dice in order A, B, C, and so on. So A, B, C, then A, B, C, again like that. What is the probability that A is the second player to get a 6 for the first time? Okay. So let us look at the breakup of this event here. So A can throw on the first throw or the fourth throw, because then second is for B and third one is for C, or he can get the 7th and so on. So you can see that the player A gets a chance to throw the die on 3R plus 1th trial for R is equal to 1, 2 and so on. Okay. Even 0 is also there, because first one also he gets. Okay. 0, 1, 2 and so on. So in order that he is second to throw a 6, it can be, so on the first one definitely he cannot get it, so it should be on, it can be on any of 3R plus 1th trial for R is equal to 1, 2 and so on. Okay. So what are the trials he is getting? He is getting R plus 1 trials, if up to 3R plus 1, because up to 3R each of them is getting RR trials. Okay. So on R plus 1 trial, that A gets to throw R not 6, and the last is 6. So the probability is 5 by 6 to the power R into 1 by 6. Okay. Then all the trials that B gets, he should get at least 1 6, because either B or C get 1 6. Okay. So B may get a 6 on R trials that are exclusive for B, with probability 1 minus 5 by 6 to the power R, and C may not get any 6 on his R trials with probability 5 by 6 to the power R. So what we are saying now, so we are saying probability that A throws A6 after B but before C on 3R plus 1th trial is 5 by 6 to the power R, then into 5 by 6 to the power R, so it becomes 5 by 6 to the power 2R, 1 minus 5 6 by 6 to the power R, and then 1 by 6. Now a similar thing will happen if you consider C throws before and B throws after. So it will become 2 times. So similar expression for C first and B last. Okay. So the probability that A is second to throw A6, and this will become 2 times 5 by 6 to the power 2R, 1 minus 5 by 6 to the power R, 1 by 6. R is equal to 1 to infinity. So these are simple geometric sums. You can easily calculate all of that. It is equal to 300 by 1001, which is approximately 0.2997. So I think you can answer these type of questions.
Yes,
Is
sir.
the proof clear? Okay. So what we do, I am just writing some more, like what is the probability that A is last to get A6 for the first time. Or he is the first, okay? That also you can calculate. So all these I am just leaving. You can calculate yourself. So I'll be uploading an assignment maybe today, by today evening or something, okay? So that you can solve all the problems, okay? Regarding the tests, we will conduct 3 or 4 tests depending upon the availability of our Moodle or other methodologies which are there. And we will have questions which will be like fill in the blanks only, because in objective type, if you put MCQ, then it is very difficult. So we will put fill in the blanks type of questions, and maybe from the next week itself we start the exam, I mean this test, because we have to do 3 or 4 tests in order to evaluate properly all the students. Okay.
So
So
whether
I
you
will
will
stop my
upload the
class now.
assignment, so whether you will be
What you are
uploading
saying?
assignment in Moodle or MS Teams?
In MS Team itself I will upload. You are able to see my previous lecture there?
Yes, sir.
And I have today morning uploaded some sheet which is just giving the section breakup actually, because students should not confuse the section. So I have put very clearly. So that also I have put there. Okay. And I'll upload these lectures again. I mean, like today's lectures also I will upload. Okay. So I'll stop the class now. Okay.